Hi everyone, my name is Abhinav and I'll be talking today about our ICCV paper CHARM3R towards Camera Height Robust Monocular 3D Detector. This is a joint work with Yuliang, Jiao Zhang, Xinyu Huang, Liu Ren and Xiaoming Liu. AVs are now everywhere, from bots to cars and also on trucks. However, the training data for training these models are only available from the platform of cars. So the problem setup that we are interested in is training a 3D detector model which was trained from car height images and deploying them on platforms which have a different mounting height such as trucks and bots. If we take a standard 3D detector and benchmark in this setup, there is an obvious observation. Changing height in testing decreases the 3D detection performance of these detectors. So why is this problem hard? Extrapolation or out of distribution is hard with neural networks. Projective transforms, because of camera height changes, are a big group and CNNs and VITs don't work. Projective transforms, in fact, are a nonlinear group and so cannot be interpolated linearly, and disentangled learning is infeasible with single height data. These 3D models are typically trained in an end-to-end fashion with an encoder-decoder framework. However, there is an alternative way to obtain the depth, which is using the ground plane. Selecting ground depth with bottom center makes depth ground dependent, and ground depth is changeable in inference because it's calculated based on camera height parameters. However, if we take and compare these regressed and ground depth 3D models, the performance of ground depth models is lower than their regressed counterparts. However, both these models show opposite extrapolation behavior. So in CHARM3R, what we do is we merge these regressed depth and the ground depth estimates to obtain the final depth and 3D boxes. Using this simple idea, closes about 45% of the gap caused by camera height changes. So the takeaways are, we mathematically prove and empirically observe contrasting trend in regression and ground-based depth estimates for monocular 3D detection, and we average these estimates within the detectors to make the detectors robust to camera height changes. Our code and the models are all public. Feel free to try them out. Thank you.